Let's touch on the available potential energy in the ocean. Obviously, you have seen tilting density surfaces and temperature surfaces already going from the deep tropics in towards the latitudes. In the atmosphere, it was the excess energy in the tropics and deficit energy in high latitudes created this tilts and created available potential energy. We said if we compare available potential energy to kinetic energy in the atmosphere, available potential energy is about 50 times higher. We had already mentioned that the ocean, in the ocean, this ratio is 400, which means the ocean is locking up 400 times more energy as a potential energy compared to the kinetic energy of the currents. Okay. So our Rossby radius of deformation is of course square root of g prime h over 2 omega, where g prime is our reduced gravity. We can write this in terms of the buoyancy frequency n, and h is our scale height, and 2 omega was our lab construct where we defined rotation omega. But we had derived this expression that APE over KE, available potential energy over kinetic energy, is 2/3 of L over L rho squared, where L is the horizontal scales of motion. What are we doing? Obviously, we are again saying to generate kinetic energy or motion in the atmosphere and ocean, the locked up available potential energy has to be released by some process. In the atmosphere, we had gone through these mid-latitude eddy arguments about how they have to move at an angle on isopotential surfaces or isentropic surfaces to release potential energy and create eddy kinetic energy. The same concept appears in the ocean as well, and obviously the scale of the eddies that are generated by the release of this potential energy is determined by Rossby radius of deformation, where the rotational forces are balancing the stratification effects, right? And we also looked at the growth rates of eddies from instabilities in the atmosphere. It's basically the growth rates of weather systems, and we said in the atmosphere that's of the order of a day. So weather systems can explode in the mid-latitudes in a day. The tropics are very different, where there is much more direct convection and movement of energy as opposed to conversion from available potential energy into kinetic energy, right? So the growth rate tau eddy is L rho divided by U, whereas U is the typical kinetic energy or the horizontal currents or winds, right? In the ocean, as opposed to this radiation forced available potential energy and the tilts in the atmosphere, the tilts are entirely created by the mechanical energy of the winds dragging around the ocean. Okay, so you remember we have wind stress curl and Ekman pumping in the subtropical gyre, and you have Ekman suction and wind stress curl pumping up the isopycnal surfaces in the subpolar gyre. So you have the trade winds coming into us here, and the westward wind stress going towards the west away from us. This is the tail of the arrow. Eastward wind stress coming at us, and that's the westward wind stress going out as well. So that's the pole, that's the mid-latitudes. So we had Ekman pumping and doming or the dipping of the thermocline in the subtropical gyre, the tilt downward here, and the Ekman suction. So the trade winds going away from us and westerlies coming towards us versus mid-latitude easterlies going westward here. So mechanically we are creating this tilt, and then we are holding it and locking up potential energy, which we call available potential energy. Main point is to remember that the ocean generates available potential energy with mechanical forcing from the wind. We will see in the thermocline circulation that in fact ocean is forced to move heat from the colder hemisphere, the southern hemisphere, into the warmer hemisphere, the northern hemisphere, because of this mechanical dragging by the winds. So the eddies in the ocean are basically again chewing up this available potential energy and producing lots of eddies. This is the Southern Ocean, which is full of eddies. For example, we looked at this before with a drifter which took some several years to make one circulation because it keeps getting trapped into these eddies. Okay, so there is a instability there. But as we said before, the eddies in the ocean in the Gulf Stream or the low latitude western boundary current in the Indian Ocean, like the Somali current or the North Brazil current and so on, are baroclinic eddies created by chewing into the available potential energy, whereas the Antarctic circumpolar current is more like the jet stream in the atmosphere. So there are baroclinic instabilities, and the eddies are being shed somewhat analogous to the atmospheric jet stream and mid-latitude eddies. So Southern Ocean is really very different in every way. Sphere group theory doesn't apply, geostrophy cannot be done, and it's more like the atmospheric mid-latitude circulation. Couple of historical characters. We talked about von Walfrid Ekman, who in one evening worked out the Ekman currents, Ekman spiral, and so on. Problem was suggested to him by Fridtjof Nansen, another giant in the field, whose goal was to go to the North Pole. He got stuck in the ice at one point, broke his ship, so then he went back with a reinforced ship hull, and he managed to make it. And he had observed that the ice flows drift to the right of the winds, and he had asked Ekman to figure it out. Ekman was working with Wilhelm Bjerknes. Remember, the Bjerknes grandfather, son, and grandson were all big names. Jakob Bjerknes was the last one who did the El Nino theory, which is really seminal work as well. Harald Ulrik Sverdrup is a Norwegian. Again, lots of oceanography came out of Sweden and Norway and so on in the early to mid 20th century. Rossby was also Swedish, I think. Norwegian, who began his career studying meteorology under Wilhelm Bjerknes. What a surprise. And he became the director of Scripps Oceanographic Institution in 1936. 1947 is where he proposed this Sverdrup theory, curl of the wind stress and meridional currents, which obviously revolutionized dynamic oceanography. Okay, so we will see a little bit more about wind-driven circulation before we close out this chapter, but you see that the ocean dynamics is very different than the atmosphere, basically because atmosphere is mostly forced by radiation and condensation heating, whereas the ocean is being mechanically forced from the top by the winds, and of course cooling and heating, creating convection in the ocean. The eddies in the ocean last much longer than the atmosphere. They can last for months and trap fish and ecosystems with them and drift for hundreds of kilometers before they dissipate their energy and disappear. So those eddies that are chewing the available potential energy in the ocean, order 100 kilometer, can last for months.